In this video, we'll take a look at a two-part example problem. Part A asked us to calculate the pH of a solution containing 1.0 molar HCN, which has a Ka of 6.2 times 10 to the minus 10, and 5.0 molar HNO2, which has a Ka of 4.0 times 10 to the minus 4. Then part B asks us to calculate the Cn minus concentration in the same solution. So if we're mixing two solutions together, the pH is dictated by the stronger acid. And in this case, our stronger acid is going to be HNO2 because it has a much larger Ka, and in this case, 6 orders of magnitude larger. So our HNO2 in aqueous solution is going to be in equilibrium with H plus NO2 minus. And as we write these expressions, a lot of the times we don't include the water, so we just show what's breaking down, and now we can write this as H plus instead of H3O plus. So then we'll set up an ice table. Initially our concentration is 5.0 molar for the HNO2 and 0 for both the H plus and the NO2. Our change is going to be minus X plus X and plus X, and 5.0 minus X for our equilibrium concentration of HNO2, where the H plus and the NO2 minus are going to have an equilibrium concentration of X. So here we can say our Ka expression is going to be equal to X squared divided by 5.0 minus X. Okay, some of the times we can do some approximations, and we can do approximations in when our Ka values are really, really small, or if so I would say smaller than 10 to the minus 5 and smaller. And then we also can look at this if we have a very large concentration of our acid. In this case, we have 5.0, which allows us to kind of use an approximation, okay? And that approximation is we're going to assume that X is going to be much, much, much smaller than 5. If we do that, we can rewrite this expression as X squared divided by 5.0, which now, if we set this equal to the Ka, which is 4.0 times 10 to the minus 4, we don't need to use the quadratic equation here, which makes the math so much easier. So if we do the algebra here, our X is going to be equal to 4.5 times 10 to the minus 2. And if we look back up here at our ice table, that's going to equal the concentration of H plus at equilibrium. So if we have that value, we can then do the pH, which is equal to the negative log of 4.5 times 10 to the minus 2, and our pH of that solution is going to equal 1.35. Now, you might be asking yourself, why can we completely ignore that HCN value? So we know that our H plus concentration at equilibrium from HNO2 is going to be 4.5 times 10 to the minus 2. Well, if we did the same ice table expression for HCN, and we use 1 molar there and set up our ice table, so it would be X squared divided by 1 would equal 6.2 times 10 to the minus 10. If we carried out the same exact calculation, we would end up with 2.5 times 10 to the minus 5 for our H plus concentration. And that would give us an H plus total equaling 0.045025, which is essentially going to give us the same pH value as if we had an H plus concentration of 0.045 or 4.5 times 10 to the minus 2, which is what we did right up here, giving us a pH of 1.35. So if we see a large difference in orders of magnitude between solutions, we can kind of skip that second step and come up with our pH value here that we did of 1.35. So this was part A of that particular problem. Now let's calculate what is asked of us in part B, which is to calculate the Cn minus in the same solution. So for this, we need to set up our equilibrium expression for HCN, which is going to be H plus in aqueous solution plus Cn minus in aqueous solution. Okay? We now need to set up an ice table for this expression, and initially we start out with a 1.0 molar concentration of HCN. We know from the previous part that our H plus concentration is going to be 4.5 times 10 to the minus 2, and our Cn minus is going to be 0. So this is kind of the first case where we saw where we do have some type of concentration, in this case for H plus. Our change in concentration is going to be minus x, plus x, and plus x because we have a 1 to 1 to 1 molar ratio, which gives us an equilibrium concentration of 1.0 minus x for the HCN, 4.5 times 10 to the minus 2 plus x for our H plus, and x for our Cn minus, which is what we're trying to solve for. So our Ka expression is going to equal the H plus concentration times the Cn minus concentration divided by the concentration of HCN, which equals 4.5 times 10 to the minus 2 plus x times x divided by 1.0 minus x. So if we assume x is much smaller than 4.5 times 10 to the minus 2 and 1.0, we can simplify our expression. And this Ka is going to be 6.2 times 10 to the minus 10th. So since this is very, very small, we can make this assumption. And by making that assumption, it makes our calculations so much easier. 4.5 times 10 to the minus 2 times x divided by 1.0 is going to equal 6.2 times 10 to the minus 10th. If we go through here and solve for x using this approximation, it's going to be 6.2 times 10 to the minus 4 divided by 4.5 times 10 to the minus 2, and our x is 1.4 times 10 to the minus 8. Okay? If we look back up at our ice table, that x right here is going to equal the concentration of Cn minus at equilibrium, which is exactly what we're trying to solve for. So our x right here is going to be the concentration of Cn minus at equilibrium, which will be 1.4 times 10 to the minus 8. And if we went through and compared this, 4.5 times 10 to the minus 2 plus 1.4 times 10 to the minus 8 is going to be roughly the same as 4.5 times 10 to the minus 2. Likewise, 1 plus 1.4 times 10 to the minus 8 is going to be 1. So we can definitely use those assumptions in order to calculate the concentration of Cn minus, which turns out to be 1.4 times 10 to the minus 8. So for our example problems here, we can go through and we can calculate the concentrations and pHs of each of the ions at equilibrium. Okay? We did examples of strong acids. We can also do, or strong acids and weak acids. We can also do the same thing for strong bases and weak bases. And we would have to use the Kb instead of the Ka, and we would get the same type of concentrations. So in the next video, we'll do an example involving weak bases.